Good morning, everyone. Thank you for joining this talk titled Neural Representation Learning in the Wild towards Generalizable Representations in Scalable Citizen Science for Brain-Computer Interfaces. And here we have Chris Simone, who is the Chief Innovation Officer and co-founder of Interaxon. Actually, this company is way more known as manufacturer of Muse, quite popular BCI device, which many of us use in our practice, trying to create a novel BCI interfaces. I'm not going to read the entire speaker's bio. It is in the meeting announcement. And without further ado, Chris, you have the floor.
Thank you so much, Ivan, and thank you very much for the invitation. It's exciting to have everyone here, so you can listen to some of the cool things we've been up to. Great, thanks, Maurice. We have a couple others on the call from Interaxon who will be presenting with me, and we will meet them shortly. So, as Ivan said, people know us as Muse, and this is because it's the namesake of our neurotech devices. And I think in many ways this kind of tension of how we're known is also observed in just the fact that we really are a very deep data and AI company, and people they get to know what they see, and that is the Muse product, which is really the facilitator in the neurotechnology space. So. The Muse device, and I'm sure some of you have seen these before, is a very simple, consumer-oriented neurotechnology device that has like a very good quality EEG and biosignals that can be used for many applications. For us, we really started in this space with the device that you see on the far left, which is a headband that goes across the forehead and behind the ears. And it was really targeted at helping people with their focus through focused attention training exercises. But we've made many other form factors of the device, and they would all share the same sensing montage, and that really keeps a consistency across our data and helps us now as we look to big data methods for machine learning. But we've also done some other things as well. We've made some very cool glasses, EEG glasses, and also we've done some cool work in VR as well. And really what we are doing is to try to build a foundation for many different BCI applications. Through our experience in the consumer space, where we're able to work directly with end users who are trying to improve their health, and we also end up with a lot of data to help us facilitate the training of better models for BCI applications. The device that is the most commonly used is this device. It's called the Muse 2. Muse 1 looked very similar. Muse 2 had the addition of a PPG device, so we could co-capture heart data, so blood flow data from the blood flow in the forehead. So there's a PPG in the part that goes across the forehead. And it's a 4-channel EEG. You wear it like this. And people have adopted it because it helps them train focused attention. So really helping someone develop their skill of attention to stabilize it, to concentrate it, because it has enormous health benefits. And this really is, has a relationship with the way that we tend to use our brains these days in a very distracted way, where we tend to jump around a lot from task to task. And it erodes our fundamental abilities of directing our attention, especially to the present moment. And so the techniques that we have leveraged really have their basis in very old traditions of meditation, but we have worked with the same techniques, but with a real-time twist. We give people real-time feedback on the stability of their attention, so that if you're able to achieve that quiet mind that's not chaotically jumping around from task to task, that you get an auditory feedback to know that you're there. And so the basic way that we would do this is a weather metaphor. You'll hear the sound of rain. If your mind is scattered, you'll hear stormy weather. And if you're able to focus and settle the mind, you're going to calm the reins and hear birds. And so there's a reward there to get people to learn in a classic neurofeedback way when the brain is in the right state. So it's a very interesting application that combines neurofeedback techniques as well as meditation techniques to help people train the skill of focus. And so you do your meditation, and then at the end, we give measurements And these measurements also help to track your brain health and performance over time. And it's something that's becoming more and more central to us as we're more strongly going into the brain health space. You might have, if you've come across this before in years past, our brand was very meditation focused, and now we're much more going into generalized brain health. And the technique is helpful. We've done a bunch of research. There's been a lot of third-party research done to look at the effect of these techniques. And no surprise, it really follows the same arc of benefit that you get from meditation training techniques of increased resilience to stress, higher attentional performance, reduced perceived stress, these kinds of things. But the learning is more engaging and it's more accelerated when you have something that can kind of hold your hand. Something that you might experience if you were to, let's say, meditate and you'd have a group that you'd go to and have a teacher, but in a way that you can actually use technology to fill that role for you. So the next really popular device that we created is this one. We call it Muse S. S can be for sleep, since we were really focusing on how we take our technology into the sleep space. And this required generating a new form factor that was super comfortable. And in many ways, we wanted to do this right from the beginning, but it was really the availability of the right material technologies that could create very, very good, flexible, stretchable sensors that could be worn comfortably night after night. And so we were very happy when all of these material innovations kind of came together, so we could actually take this new direction. Our interest in helping to support health, obviously, sleep is a pillar of health. You can't really help yourself much if you're not sleeping well. And we really believe that there was a lot we could do to facilitate better sleep. The utility of it for the end user, I mean, the first part, sleep tracking, that's quite obvious. And as you might expect, we can track the stages of someone's sleep, their sleep position, their heart rate, these sorts of things. One differentiator is when you have access to the brain, you can actually do very, very accurate sleep measurements. And so something that we've been able to achieve is to have a sleep measurement accuracy that's the same as you would get is if you would go into a clinic, do an overnight PSG in a lab, and then have an expert stage your data. And that's very helpful if you're actually trying to use this as a tool to help give you feedback and improve your sleep and your behavioral patterns around sleep, because you can actually, be assured that you're actually seeing the changes that are, truly happening, as opposed to might be happening, as you might find if you were trying to use, let's say, an actigraphy device or a PPG-based device to analyze your sleep. But the other thing, and this is really kind of in our core in the Muse DNA, is the sort of real-time applications. And so we really had a strong belief that we could create something to help people take themselves to sleep more effectively. We knew, especially with our work already with the Muse device for meditation, that many of our users would bracket their sleep either at night or in the morning. And those who were using it at night, really, they were doing it because it helped them go to sleep. And it was really about calming the brain. And going deeper into the challenges people have when they sleep, insomnia is really a huge affliction for many people, adults in the population. And then we have so many others that are subject to mild insomnia, which is like having trouble falling asleep or waking up in the middle of the night and having trouble sleeping again. And the biggest culprit for that is having a busy brain. And the busy mind is really something which is stimulated by an emotional process. So often the feeling that we have generates thoughts, and the thoughts generate more feelings, and you go on and on. So how do you break that cycle? And so we created this thing called the digital sleeping pill that was really based on our ability to track that transition from waking to sleeping, so we could intervene in creative ways to help people detach from that cognitive process that's keeping them awake. And the simple story of how that works, Maurice will talk more about this later in the presentation, but the simple idea is if you can get someone to step out of their present moment experience and into something else which is less provoking, so maybe not feeding back an emotional process and thoughts that intensify an experience, but rather allow you to ride along in another experience. A great example is listening to a story. That can actually give someone an opportunity for sleep, because once you detach from that energizing discursive thought process, this is when you feel tired and you start to doze. And dozing is something that, we go from consciousness into semi-consciousness. but we're not really falling asleep. And we found that if we could detect those subtle moments, that we could actually go in there and change the audio experience. You can imagine if you were a parent reading to a child, if you're, reading a bedtime story, what you'll do is you'll actually watch to see, is there a potential you might fall asleep right now? And if there's a possibility, I'm going to stop reading for a moment, or I'll slow down, or I'll change the tone of my voice. And these cues create space where the mind, without something to hang on to, sort of falls asleep by accident. And having an AI that can predict this to happen, and to have a more nuanced measure of these kind of micro states between waking and sleeping, really facilitates the creation of a technology that does the same thing very effectively. So that's kind of our last device in its innovation with the digital sleeping pill. We just launched a new device, and it looks almost the same, but it has some really cool differences. We've incorporated an fNIRS array, so we can measure EEG, which is measuring the electrical activity of the brain, but we also measure the blood flow and oxygen saturation in the front of the brain, and this is called functional near-infrared spectroscopy. We've expanded some other things. It measures SpO2 now, which is very important for sleep apnea. And we can also do ERP measurements. So the array that measures the fNIRS, if you look at the image on the right here, we have EEG electrodes. These are the silver parts on the front of the headband. And then you'd have these 5 windows. In the middle is the emitter optode. And you have 3 different wavelengths of white light emitted from there. You have red and 2 infrared wavelengths. And then you have on both sides, you have 4 different detectors that measure both the short channel and the long channel light that's flowing through the skin and then through the deeper tissues, including the brain. And then looking at those is really what allows you to kind of decode that blood flow through the brain measurements. So I'll just give you an idea of what this looks like. So this is a simple example. So brain activity. So if you're engaging in a cognitive task, that's going to affect your frontal blood flow, but also different breathing techniques also affect it, which is also no surprise given how prevalent different breathwork techniques are now, coming into vogue. But on the left, you have just very simple deep breathing. On the right, you have a sequence of breath holds. And what you see when you measure the blood perfusion in the front of the brain is you see, these disturbances that are caused by these respiratory effects. So we're seeing here the red lines are oxygenated hemoglobin and the blue lines are deoxygenated hemoglobin. And you're measuring blood concentrations here. The other thing I mentioned, and I think those of you who are in the EEG space, you'll know what ERPs are, but basically when you present a stimulus to your senses and you have a task to do, if you actually measure what happens in the EEG, time synchronized with those tasks, you actually see repeatable patterns of polarization and depolarization in the electrical brain activity. And you can measure those, and there are very useful measurements that you can make from that have been done for years and years. One of the challenges is you need to have very good time synchronization between the measurements and the stimulus. So to make this work, we need to create protocols to do clock synchronization between the Muse device and the mobile device. So getting the clock synchronized between the OS clock, and the Muse clock. And then you need to also be able to predict, when you say, okay, draw the green circle on the screen, knowing exactly when that'll be presented. And there's also this rendering pipeline. So there's a bunch of unknowns you have to solve for. But once you do that, you can have very good time synchronization between stimulus and the measurements. And that allows you to do these very cool way of looking at brain activity where you can look at this sort of millisecond response. It's actually more hundreds of milliseconds, a response to the brain, and make the measurements that have become so common in the EEG science and how that relates to things like attention and other processes in the brain. So, oopsie, click next. So this kind of just is like a high-level map of the evolution of our technology from a device perspective. And we've tried over the years to expand on the sensing capabilities, but the whole time we're keeping the montage EEG montage or the locations of the sensors across the device is the same. And this allows us to have harmony across our whole data set, which is quite important as we're looking at building models. You can build single channel models, you can build channel agnostic models, but also if you're able to use the spatial dimension of the data, it's more powerful. So we've really tried hard to keep the data consistent across the different generations of our tech. So, okay, so I'm just going to take a step back. I mean, this was the sort of hardware perspective of Muse. And one thing I just wanted to kind of, stage is that, overall, we have a much bigger mission around health. We have a deep belief in the power of the data with these new AI technologies to really help us in many dimensions of our brain health. So our consumer apps, they already touch upon these pillars like sleep and recovery, mental health and cognitive function, which are really supported by these techniques of meditation. But there's a lot more that's possible. And the challenge has been the creation of generalizable algorithms and more sensitive algorithms so we can actually do measurements that are going to help to unlock some of these categories, whether it be for a therapeutic intervention or for a diagnostic. And so from inside of Muse, the company, specifically working with the data, developing AI pipelines, and working, with the latest in the machine learning methods is really where we have our focus. And we will talk about that. And so there's a lot actually that's in our platform besides the kind of the device that you see, and this is like a huge database. We have over 1 billion minutes of EEG, which is very exciting for those who are into self-supervised learning techniques and big data. We have a great AI infrastructure. We do biomarker development. We have pipelines to do real-time diagnostics and measurements in the app. We also have cloud pipelines for that. And that allows us to have this whole kind of like clinical and research arm to our business, which is super interesting. And we also have an SDK that helps people and then build upon the tools and models that we build. And so a big part of this, and we'll talk more about this, is the creation of a citizen science platform. And the genesis of this really came from the understanding that if you're going to build therapeutic interventions that help somebody with their brain health, how do you know you're building something that works and how do you optimize it? And it's not something you can do with like 20 people in a lab, which is traditionally how neuroscience is practiced, very small sample sizes. And, when you consider the complexity of the brain, the complexity of our behavior, that's nuts. And the only way to really do this properly is to really be able to take a scaled approach at it, where we can really involve many people to try different things and to see what happens. And so we're very lucky. We have an extremely engaged user base that are very interested in pushing the science and also pushing brain health. And so we put advertisements out saying, hey, do you want to participate in the study? And we get thousands of people sign up where we can actually do brain science together. And so we built an infrastructure in our app, which I could talk a lot about. And it allows us to deploy experiments, just like you deploy content. So it doesn't involve app changes. You literally just download protocols from the cloud, and you can have, learning questionnaires, cognitive tests, and real-time interventions where you can have like this whole real-time adaptive system, like what I was describing with the digital sleeping pill, and be able to try these things and change the parameters of these interventions across different user groups and to evolve this in this more human in the loop kind of machine learning approach. So this is something that we're quite proud of, and we're actually leveraging a lot now. We work a lot with academics in research groups as well as other companies that are trying to get in there and learn more about what's happening at scale. And it could be everything from like a digital intervention to a psychedelic therapy to a drug therapy or a CBTI approach. So there's a lot that you can do once you can kind of have this sort of at-home, deployable, easy to use, decentralized study approach. Okay, so what are we doing with that? I will hand it over to Ervin to kick us off as we get into what we're doing on the AI side.
Thank you, Chris. So as Chris mentioned, in this next section, we will explore how we are moving towards generalizable neural representation learning with EEG. And specifically, we'll look at the need for models that can adapt across individuals, tasks, and real-world conditions. So Historically, EEG analysis relies on the manual feature extraction that requires domain expertise, and typical features extracted are like band powers and other features that are then fed into classical machine learning models, such as a linear discriminant analysis, LDA, or a support vector machine, SVM. But what we've observed is this fails to generalize across individuals and sessions, and it's also not very robust to noise or hardware variability. And on the right side, we see the needs for a consumer scale neurotech, and we show some of the challenges where there are different settings, there are different applications, there is sleep, there is meditation, there's daytime use, there's also different types of hardware. And so there's a lot of inter-subject variability and inter-device variability that we need to take into account. So EEG signals, they vary in all these conditions. And so there is a need for methods that can extract invariant and generalizable representation, regardless of when or where the data is recorded. So at Muse, we've collected an enormous amount of EEG data through the participation of our community, both during meditation and other wakeful states, as well as during sleep. And this large scale brain data, it allows us to go in these two different pipelines or complementary systems. One, we call it the normative EEG database, where in this database, it helps us to benchmark an individual user by comparing their characteristics and typical patterns with the rest of the population across different age groups, gender, sleep profiles, etc. And then on the other side, we also have foundation brain models, which are built using self-supervised learning on large volumes of unlabeled EEG segments. So these two pipelines help us to learn some of the representations that can generalize across different states and tasks. On the bottom here, we have a visualization of the brain embeddings in a two-dimensional space, and this was a model that's projecting the data from our sleep EEG. And we can see very nicely these different stages of sleep, the wake, N1, N2, N3, REM, all of them being nicely clustered on this two-dimensional representation. So currently, foundation models are needed for brain health. And why now? There are a few converging factors. So firstly, it is the data. We now have unprecedented amount of data, access to large-scale EEG recordings from real-world users, and something that was not available even just a few years. There have been advances in GPUs, parallel processing that make it feasible for training such large-scale models, and also methods such as self-supervised learning that has really matured. And now we are able to adapt these techniques that were typically used in natural language processing or computer vision applications, bringing them into the domain of biosignals and EEG. And lastly, the clinical and consumer demand. There is a growing demand for scalable, personalized brain health tools, not just in the labs, but in the homes, in clinics and wellness platforms. So putting all this together, we call this new class of generalizable models as foundation brain models. And what makes all of this possible is self-supervised learning. And as most of us know, self-supervised learning leverages the inherent structure in the data to create toy problems, which are also known as pretext tasks. And that will let the model to learn these generalizable representations by solving these pretext tasks. And a classic example in the LLM case is to predict the next word in a sentence. Similarly, we apply those principles in EEG, and by solving these tasks, for example, EEG is processed in segments or windows of data. So if two segments are from the same user, or if they are correctly ordered in time, this information can be used to train a pretext task, and the model learns this rich representation. And once we have this representation, we can then use them in downstream applications such as like sleep staging, apnea detection, event classification, state classification, and so on. And soon we will see an example of a study that we have conducted internally.
Arvind, can I
Yes.
ask a question now, or you prefer this to happen after the talk?
Either ways is okay.
On the previous slide,
Yes.
how big is the large brain data corpus, and how you obtain it?
Yeah, that's a very good question. We have a slide actually showing you the size of the data set, but what we have done is we used a subset of about 80,000 sessions, approximately from 18,000 users as a preliminary analysis. Yeah.
Okay, sufficiently large for unsupervised training. Thank you.
Yeah, thank you. So typically as pretext tasks, these two methods are typically done in the literature. We have one called the relative positioning, another is the temporal shuffling. The relative positioning is quite simple. We have several windows of EEG. We have an anchor window and then define a time. If a particular window falls within your positive time window, we call that as a positive example. So if windows are close together, it's a positive example. If windows are further apart, it's a negative example. And this way, when we train the model learns to capture temporal continuity in the EEG. In the case of temporal shuffling, instead of two windows, now we go to three windows and we order them in a certain way, more like solving a jigsaw puzzle, where there are three windows in sequence and then the order is shuffled. And so positive example is windows in sequence. A negative example is if the order is shuffled. And so now the model learns to find the temporal transition and structure between these two examples. Another interesting approach that has been used is the contrastive learning. And contrastive learning is trying to bring similar samples close together and dissimilar samples further apart. And so with this, we have explored two different approaches. There is one at the segment level, and then there's one at the participant level. At the segment level, we take two segments. We take one segment of EEG, corrupt this with noise, and then we give it to the model. And we want to say, okay, these two are similar segments. And then you take a completely unrelated segment and say, this is a dissimilar segment. And so this way, the goal is to learn features that are robust to noise. But on the other hand, there's also inter-subject variability with biosignals. So the participant level pretext task is actually quite beneficial in this case, where two windows coming from the same user are positive pairs, and a window compared to another user is a negative pair. So with this, we have run a study, and this has been currently accepted for publication at the IEEE EMBC conference. And based on that pretext task, we use two different backbone architectures for the foundation models. One of them is the shallow net. The other is the EEG conformer. The shallow net is what is typically used in BCI literature. It's well understood to emulate the filter bank analysis. So there's temporal convolution followed by spatial filtering. And then in the case of EEG conformer, it's actually the same shallow net with an additional transformer encoder. So now once we train this, we can use the representations and embeddings to train linear classifiers to probe the performance. And in this case, we used a couple of example tasks. This is primarily the downstream task for predicting the age and sex from a given window of EEG. So what we see here on the top left is we are seeing that with a larger pre-training data set, the performance improves. But then on the right side, what we wanted to mainly compare was the difference between the methods. So we proposed this new method of participant level pre-training. And we see that with both the shallow net and the EEG conformer, the participant level pre-training improves the performance compared to just using the segment level pre-training. And most importantly, the linear models that we are using, although they are simple, we're able to see that on the bottom two graphs, that especially in the low label percentage regime, that the pre-trained model does much better than a model trained from scratch. So they show us encouraging trends, especially in the low label settings. But it is also worth noting that like the downstream task of age and sex classification, like this is not the end goal, but definitely they offer a lens into like what is the strength of learning this kind of representation. And we're really only beginning to scratch the surface. And this kind of answers part of your question, Ivan. We only trained this on 80,000 sessions, but with more and more data, we can actually improve the representations, the generalizability, and also across different tasks. And next, what we'll do is we'll look at how we are leveraging not only the raw data, but also our normative database for example, brain age estimation, longitudinal tracking, and also some emerging directions such as emotion state classification, which is a future work, something that we are excited about. So one promising example is to estimate someone's brain age. And this is a biomarker of brain health. And what we are using in this study is to extract features from sleep EEG, such as biomarkers such as sleep spindles, slow waves, and spectral features that have been known to show this trend with age, and they shift with age. So there is a potential in extending this towards AI-based early prediction of cognitive decline. And another exciting frontier is we have, as Muse, we have the simultaneous biosignal along with natural language data. So biosignal with EEG, PPG, now fNIRS. And we have users going through the guided meditation and sleep stories. So this offers a good connection between language, physiology, and self-reported emotion. So in the future, we could use the embeddings from the foundation model to model how these emotional states evolve, and they would open a door towards like adaptive emotion-aware experiences. And this remains a promising direction for future work. And another very good example is how we leverage the normative database to have a longitudinal view of data. And what you see on the left side here is we have run our automated sleep staging algorithm on a large population, and we see the percentage of sleep stage of different sleep stage across age. And as expected with age, with aging, we see an increase in stage 2 or light sleep and a decrease in the deep sleep or N3 sleep. So we can now perform these kind of comparisons. And then on the right, we have two more examples, which is looking at micro events in the sleep, such as the slow wave density and spindle density. And here, for example, we're looking at the distribution with two different age groups and then a particular user's age group and being able to compare them with respect to the population. And since we are now on the topic of sleep, let's explore how we apply these large-scale data sets to build automated sleep staging models and investigate their roles in diagnostics. And so now I will hand it over to Maurice, who will walk us through the next section.
Thank you, Arvin. Yeah, that detailed sleep tracking that you showed is actually very important. As Chris mentioned, we're very interested in brain health, and sleep is not something that's just beneficial to you. It's actually a fundamental pillar of our brain and mental health. But actually, many people struggle significantly with sleep. In fact, for example, clinical insomnia impacts an estimated 10% of adults. I actually was shocked when I learned that. And if you suspect of having a sleep issue, what you typically have to do is you have to go to a sleep lab and get what you would call a polysomnography or a PSG. So basically what happens is you get hooked up with a bunch of different sensors that measure your brain and also your breathing activity You have to sleep there overnight, and then there's a sleep expert that's going to come and painstakingly look and sleep score your data. And probably, as you can imagine, this is time consuming, it's expensive and labor intensive, and really like sleeping in this way is not really representative of your true sleep. So what we aim to do with the Muse S that Chris presented is changing the way this is done by simplifying and bringing this technology at home. So the Muse S can actually collect brain and heart data at the comfort of your home and can send that data to a mobile app that analyzes it in real time. And in order to do that, we would need to build these machine learning models that run in the app, and that automate the tasks that a human sleep expert can do. And when you're building such a model, it's not just about performance. There's a lot of several considerations that you need to take into account because you're developing something that will be used at home by consumers with minimal supervision, unlike if you're at a sleep clinic where you will be actually supervised. So you need to, your machine learning models need to be robust to transient nodes and bad channels that are caused by motion artifacts or a bad headband fit or sweating, etc. The model needs to be able to be running in real time to enable these adaptive neuromodulation application that Chris was talking about. And the model should be able to be packaged in a form that is able to be run in the app. And that means it doesn't have to be computationally too intensive, and at the same time also memory friendly. And finally, since we want this to be used by thousands and thousands of people, the model has to be calibration free and generalizable. So with all these constraints in mind, we designed a deep neural network that has been trained to effectively get detailed measures of sleep states. So our models consist of hybrid convolutional neural networks, or CNNs, and recurrent neural networks. In this case, unilateral long short-term, unidirectional long short-term memory network, or LSTM, that enables these real-time applications I'm talking about. So the CNNs, they look at the raw EEG data, and they're going to extract features from this data. These features are then passed on to the LSTM, which models the temporal dynamics of these sleep states, and also narrows down your current sleep state to based on the features that are extracted from the CNNs. In the CNNs, we have different kind of filters, convolutional filters. We have small and large time windows, and that's designed to be able to see different kind of EEG features. Also, the algorithm we have multi-channel and also single-channel models. And we have an ensemble aggregator that takes into account the signal quality coming from the channels and also the outputs coming from these models, and weighs the contribution of these models to the final output. And because of that, we are able to get a measure of sleep states, even if only one of the channels is working well and the others are not. We have also something called a dynamic spatial filtering layer, which is essentially a multi-head attention module that is plugged before the first layer of the multi-channel model. And this layer here, it really learns to focus on the good channels and ignore the bad ones to reduce the effect of noise on the subsequent layer of the models. And to make our model even more robust to noise, because now noise is really an issue, especially when people are using it at home. So we injected, during training these models, we injected noisy data into our model. So we injected white noise, but also we injected noise that we took from our real world data and injected that randomly in a random fashion during our model training. And since our models have several layers, the deep embeddings that are in these layers can serve as representation that can generate more nuanced and continuous insight into someone's sleep state. So, and also to be able to look into what the model is doing, we have methods like GradCam, for example, where you can kind of have an idea of what the model is looking at to measure sleep states. For example, when you're in light sleep or stage and 2 sleep, we are seeing that the model is looking at these signatures of light sleep, which is called K complex. Great, so we package this algorithm into the mobile. It's running inside our Muse app and also in the cloud. And now someone can go to sleep night after night and get a detailed analysis about their sleep at home. But how do you validate that this kind of sleep analysis is working well? How do we know how performant our model is? In particular, how does the output of our sleep analysis compare to the outputs of a sleep expert in a clinical PSG, where the sleep expert is assigning a sleep score, wake, and 1, and 2, and 3, or REM, and producing something that we call a hypnogram. Well, our model is also able to work the same way and on the same sleep segments that the sleep experts are looking at, producing its own hypnogram for your entire night. So now what you do actually is you have to go to a sleep clinic, you wear both the Muse EEG and also the PSG system at the same time. Then you would have an expert sleep technologist that will score the PSG and give you your golden labels, your standard sleep labels. And the sleep analysis model would output the automated sleep stages, which could then be compared to the gold standard. And this is exactly what an independent group at the University of Ottawa carried out with a cohort of 47 participants and included good sleepers as well as people with sleep apnea. And what they found is that the overall Cohen's kappa of the automated sleep algorithm against the PSG is 0.76. So what's Cohen's kappa? Cohen's kappa is just a measure of accuracy that is adjusted for chance. And what these results mean is that the Muse achieves expert level sleep staging. Because if you get 2 human sleep experts and you have them analyze the same recording, they will not agree 100%. They will agree on average with a Cohen's kappa of around 0.75, or roughly 82% of the sleep stages. What the study also showed is that the core recordings validated that the sleep landmarks that we typically see in a PSG, like sleep spindles, slow waves, eye movements, can also be seen on the Muse EEG. Right, so great. We have this great sleep model that can be used to sleep score Muse EEG as accurate as sleep
Maurice,
experts
can
see
I
the
ask
PSG.
you a question
Yes,
before you go? So 2 questions. First, when you train the classifier, what are the labels?
So the labels in this particular case are the sleep stages. So
Okay, how you obtain them?
Yes, so great question. So since the landmarks of the sleep stages, for example, you can see the spindles here, the slow waves, the eye movements, alpha and wake, they're visible on both the PSG and the Muse. So when we developed the model, we had the sleep experts hand score the Muse EEG. So they can look at this, like, okay, this is N2, this is N3, and we use the labels from the sleep experts staging the Muse to train our model.
Okay, but there are not that many. You lose the advantage of having a large data set when you count only on the human labeled segments. Anyway,
That is true.
My second question is this model a person dependent or person independent?
So this model is totally person independent. It would work on any person.
Perfect, thank you.
Thank you, Ivan. And that's a very good question. I mean, also, that's an important thing to consider during testing. So when we developed our model internally, our training, the subjects we use for training are not included in the testing. So when we test our model internally, we made sure that the recordings and the testing sets are from people that were not seen in the training set. And also, when these people did this independent study, the people that they had were totally unseen by our training. We didn't know about it, and there's no calibration, nothing to do. It just works right away.
Very nice.
Thank you for the questions. So we have this algorithm that can do the sleep staging, but we want to go beyond that. How do we go actually beyond that and use the representations that this model learned to support adaptive modulation application, but also unlock deeper understandings of our sleep? So to do that, you can look at the inner representations of the sleep model. And what we actually found is that the model is learning nuanced and continuous measures of sleep. For example, if we look at the embeddings of the Muse sleep EEG using a technique called UMAP, we notice that our model internally reveals kind of a sleep continuum with a large N2 cluster, which flows into N3, your deep sleep, flows into REM, also known as this period in sleep where you're actually dreaming, and also flows through N1, through this stage here in light gray that you see that is called classically N1, and more informally, the hypnagogic states. Now, that region here, this transition from wake to sleep through N1, is actually pretty important for the process of you falling asleep. And in fact, in classical sleep staging, this stage here, so here you have you're awake, you have your alpha, then your alpha starts disappearing, and then you have your spindles that appear. This transition here between the wake and your N2 sleep is called N1. And even within that state, people are trying to divide that period into microstates based on different EEG patterns. And while this is still a poorly understood area, like one proposition was to divide that here into 9 different states called the Hori stages. And when we looked at the output of our sleep model versus the Hori stages, we see that our outputs are effectively tracking these Hori stages. Therefore, kind of confirming that there is a sound and scientific correspondence between what people have been noticing before with these Hori stages, but also what our model is learning and the deep representation that our model is learning. This also means that we can use our model to track a person's transition from wake to sleep and offer these neuromodulation based on our sleep model's output, which actually led to the genesis of our digital sleeping pills that Chris talked about. So these digital sleeping pills, or DSPs, effectively are using our sleep model's outputs and auditory neuromodulation to guide the person to sleep. And we deploy that in our app, people are using it, and we ask ourselves, how well does it really work? And how well can we improve it? And this really spurred us to build that platform that also Chris talked about in the beginning, where we can leverage our community to test our algorithms and get feedback. So with this platform, we are able to do decentralized studies, upload different protocols, algorithms, contents to the cloud, deploy them in the app, and really collect data from our users at scale. And we use that platform to test our digital sleeping pills. It was actually the first study that we did using that platform. And we advertised for a couple of weeks, and we enrolled 160 participants. And we distributed them in different groups. And they collectively went through a week of sleep recordings and questionnaires where they reported details about their experience. And really, in a few weeks, from advertising to data collection to analysis, we were able to do this study. And we found that people loved it. So kind of compared to a control group, the groups who used DSP, they subjectively and objectively had reported easier times of falling asleep. And not only that, but we also got reports about their conscious experience, and that gave us more insights and more confidence in what we have built before and we are building now. And I see that Chris removed his camera.
I love talking about this stuff.
Okay.
Yeah, I'll jump in here just because I love it. So, this is sort of like the first foray that we made into sleep improvement, and I really love this kind of technology generally for sleep applications because we are asleep and there's very little action we can take on our own to try to intervene and improve our experience. But there's a way for technology to get in there and to really assist in many different ways. That's very cool. And so, this is like what we have a picture here of on the slide is some of the ways that we are exploring. And we're not the only ones doing this. And we have like an amazing array of researchers that we work with that are working on some different strategies. But there's very cool things you can do. Everything from entrained stimulation during deep sleep to improve slow waves, to having ways of waking someone up so you feel more refreshed. So getting woken up at exactly the right time or staging someone out of sleep. Sort of the opposite of what we do because we try to put people back generally with our digital sleeping pill. And then there's all kinds of cool things you can do with dreaming as well. So an example of that is, what's sort of generally termed targeted reactivation, where you can actually have somebody prime themselves during their waking hours. And this can be a visualization, it can be even a video or a narrative. And then you would combine an audio stimulus, like a certain kind of bell sound, with that experience. And then by presenting that at different points in your sleep, you can achieve different effects. So, for example, presenting this stimulus during the right times in deep sleep can actually improve memory consolidation. And presenting this in a dream state can actually bring this kind of content into your dreams. You can think of it as like a dream engineering. And this is particularly helpful if someone is experiencing nightmares. If you're suffering from depression, as an example, you'll often have nightmares that are recurring. And this is a way to help to re-guide the brain. Or potentially you're just interested in trying to use your dream time in some beneficial way. So I feel like there are many possibilities there, and we're just kind of getting started, but we definitely know through the research that's been done that there are many powerful things you can do, including helping someone to reach a lucid state where you actually become conscious that you're dreaming within your dream. And that in itself can be very, very interesting for someone to peer into that subconscious process. So lots of fun to be had here. But generally speaking, we have like a intelligent model. In this case, we're using a model that was trained for sleep staging, but we can use that sort of underlying representation to kind of get a finer tuned idea of what's happening in the brain processes. And we can link that to another kind of adaptive, intelligent model that can have an end application, be it sleep induction, dreaming, or diagnosis. And so another example of this, which is quite cool, and this is something that we've been started working on recently, and it's wasn't created by us, but it's a really interesting idea where you can train another model where the input is not EEG, but in this case, it is sleep state, so those sleep stages, and looking at that sequence that happens throughout a night, kind of like a word. And in this case, a GPT-2 model was used, and it was trained to predict the next sleep stage. And the model that was learned during this showed some very, very useful characteristics. I mean, one of them is you were able to make corrections to a hypnogram. So if you had noise in your data or other problems, you could improve its performance in the case where you're not able to have appropriate classification because of some issue, and be able to do quite a good job at that. And then you can also use this for other things like diagnosing some kind of sleep condition. And the beautiful thing is the interface between these two models is super simple. In this case, you just take the sleep stage output of a sleep staging model, and you can pass it into a subsequent model, which can now make an assessment based upon the learning the dynamics of sleep stages that you can find in many open data sets. And this particular group used a whole bunch of open data where sleep architecture, so the sequence of sleep stages, was associated with different medical sleep conditions. And that provided the foundation to train a model like this. And so the availability of data, enabled this kind of model creation. But I think generally speaking, this is the thing that we're kind of most excited about right now is starting to connect different AI models together. Like you could think of it as like a model stacking or model augmentation. And specifically, something which is very obvious and very easy to do is to start to connect these kinds of brain model measurements to language models. So in our application, we have users that are using our application. They make measurements and they want to know what it means. And they want to know what it means in a way which is related to what they're actually trying to do and what they're experiencing from day to day. And just by creating good combined prompts where you take information about someone's brain state and you combine this with essentially the equivalent of help this person understand their brain data, you actually get narrative descriptions that really help the translation of this information to somebody. But then also you can actually create real-time experiences where you can embed with your prompts, okay, like what is happening with someone's stress level, with their attention, what's their heart rate, and that can be combined in a very simple way to how we can improve this interface between a language model, an individual, and a brain model. But I think this is just like the simplest way of doing it, and we're all witnessing the power of some of these models that have been trained for different purposes, especially on the language data. And the question is like, what can we do with that? How can we use this approach to actually start to investigate what a brain model has learned? It's not an easy question to know what a brain model has learned. I mean, you try this with downstream tasks, but it's like, what did a language model learn when you trained it in all this data? What's useful about it? And it's not so simple. To try to sort of peer into it and really see like, what is truly there that's valuable. And so I think, one question is, what is the right way of connecting these technologies together? Can you train a representation that facilitates the connection between different AI models? How do you teach a brain model to speak in some way that can be understood by something else? So I think there's a very rich, research question here that we're just getting started on. And it's something that I would, love in our Q&A session to even, just take a stab at together of, what are some strategies that can be used to start to do this kind of model augmentation or model stacking, because I think there's, fantastic power that's available there. Okay, I'm gonna actually pause there. This is sort of the technical conversation that we hope to get through. And I would love to make this opportunity now for Q&A and to explore it together. Ivan.
So, thank you, Chris. First, thank you for the wonderful talk and for the information. I will let the audience ask some questions, and also I have my own. So, colleagues, questions? Feel free to unmute and ask in speech or type in the chat. Actually, there is a quite active exchange and questions and answers going on in the chat.
Yes.
Questions?
Just wanted to highlight, there are like 4 questions from the chat that I have highlighted, but I can, leave it for the end after the verbal, pieces of the questions are done. I can highlight those one by one, and we can get into them as a group if we want as well.
Okay, it's fine. If you think, by the way, thank you for answering all of those questions in the chat. But Taha, if you think that there is something to be commented on the questions in the chat, please feel free to do it now.
I think I highlighted some general replies. I think what's left is maybe just punting the question to the crowd. It's not much of a direct response that's not in the chats right now. So yeah, basically, if do we want to get to the chat questions in that case, one by one, shall we?
So go ahead while somebody asks questions to comment on the questions in the chat.
Okay, sounds good.
I'm just trying to catch up on these chat questions. So if anybody has a question to add to the mix, feel free.
Dimitra raised his hand.
Dimitra.
Unmute.
Oh, yes. Okay.
Oh.
Thank you. Thank you for this wonderful presentation. I had a couple of, I guess, more technical questions and more high-level questions. For the more technical question, in the self-supervised learning, how do you approach potential missing channels over all the data that you aggregate, or even missing epochs or time segments?
Yeah, that is a very good question. We have developed an internal signal quality classifier, and what that does basically is look at the spectrum of a window and then fits a line to the spectrum and looks at the slope, the offset, some of these characteristics. And while training, we only train for the SSL alone. We only look for good epochs and we train that. And we also want to make sure there are all 4 channels available. On the other hand, for the sleep staging model, we actually use the outputs of the spectral signal quality classifier because in real time, we want this to work out there in the field. So we use the outputs of that and then we mask the data and we mask certain portions or certain channels while running the prediction at inference time.
Well, thank you. Another question I had, you talked a little bit, I think it was slide 28 or so, about the age and sex prediction using ShallowNet and one other architecture. I was just wondering, how close are we in identifying persons from EEG? Because the reason I ask is because that will make our RB approvals really difficult in the future. So if you had any insights on that.
That's a really good question. It's something that we are working on right now, to be honest, because we are, as the training task is a contrastive learning that would, should yield a model that's very good at discriminating people. We do see that the data clusters very tightly around people. And it's a real question of how that might work in a generalized setting with, like many thousands of people. But I think that's a question that we're trying to answer right now, because, you do see that the data clusters very, very tightly around individuals. You see all of their sessions and brain data clustering on top of itself. When you just take this sort of like, generalized view at how the embedding looks. And you can also see that like in how the accuracy of the age and sex classification, that kind of general distribution of the embedding space is also visible, because we're just using a very, very simple linear classifier. And the models that we have are really more focused on separating individuals from each other. So it's a great question, and I think that if you have enough data, it's the prospect of identifying people is extremely high, for sure.
Oh no! Oh
Yeah.
no!
Yeah.
More questions? I have a general question regarding fNIRS. So I suspect that most of the data and results you show it are based on EEG data collection. What is the status in the situation of fNIRS? How much useful it is for sleep and for other applications, and what do you guys do with it?
That's a great question. Kind of ask us in a month, because one thing that has been very difficult with fNIRS is the availability of co-captured data, EEG and fNIRS. And we just launched, right? Like this product, people are just receiving a couple of weeks ago was when the first people received their new devices. And so we are, very, very interested in this question. One of the challenges with fNIRS is, and it seems to be even more so than with EEG, is very sensitive to things like head orientation, blood pressure changes, temperature variations. There's a lot of things that affect the signal, and so it's very hard to make a naive assessment without a block design. in how you look at the signal. So you can have essentially like an A/B comparison that you repeat. But that's one thing that we're really hoping to see start to change as we get more data, because we'll be able to build representations that can kind of look over some of these transient effects. But you wear an fNIRS device, you tilt your head on the side, and the signals change. Because the hydraulic system has a variation in it, which makes obvious sense, but until you see it, it's you don't realize how big of a problem that is. So we're using it primarily in a neurofeedback training approach, where you're getting someone to increase the activity in their prefrontal cortex, because we have seen therapeutic effect from that is truly useful from a brain health perspective. But I think where we have the same question, it should be very helpful, because the EEG gives you this very generalized high-speed response in the brain, and fNIRS gives you a highly localized response. It's slower to respond, but you're looking specifically, I mean, we're looking at the prefrontal cortex, which we know is heavily involved in many very, very important parts of cognition. So we call it the executive center. And so I think, combining this sort of generalized EEG and this localized fNIRS, should really have some very good applications. But great question we have also.
We also agree that fNIRS should have its own applications. We still don't know where exactly is the strongest. It has pluses and minuses, advantages and disadvantages compared to EEG.
Totally. Yeah. I think.
Go ahead, please.
Go ahead, Evan.
Last week, Dimitri and I published our first paper using fNIRS for workload estimation.
Fantastic.
And we had some interesting finding, and of course, that was with a full head gap with fNIRS sensors. But it will be interesting to see what can be achieved with a super sleek and elegant design of Muse for other scenarios besides sleep and detecting the sleep apnea. And that actually leads to my second question. How open is the device for usage different than what you guys designed it for? Can we have easily access to the raw data?
Yes, absolutely. Yeah, it's very easy to connect to the Muse device and all the raw data streams without any pre-filtering. And that can be used either in a mobile app, we have an SDK, or we have tools that just connect to the device and you can use it on your PC platform. It'll connect to the device, it'll stream the data over LSL or OSC, and that can be interpreted real time. So there's a lot of ways to connect to the device that are open and easy to use.
So, Chris, let me clarify this. The data from the device go to my computer. They don't go first to your server and then back to us.
They don't need to.
And they're not shared with you without our knowledge.
Right. Exactly.
Because for certain data collection, it will be super difficult to obtain ethical committee approval if the data was uncontrollably shared with anybody else.
Yes. Yeah. So there's easy ways of using the data, using the device in that way. The main reason why people like to use our application is if they want to do a broad deployment. And so if you wanted to, let's say, put an experiment in the hands of 1,000 people, the way to do it is, through our community. And then we have very easy ways to do that, in which case the data does flow through us. And, we work with a lot of universities, and, there are various ways of structuring those experiments, including, an agreement where we delete the data from our databases, but it does flow through us. So, we haven't had a problem with this, but it could be that some ethics, boards may have trouble with that.
Our impression with Dimitri while writing that paper was that there are not large data sets available using fNIRS. There are no foundation models for fNIRS. Even the future set is kind of not that well established. Neither is the pre-processing. It's different land than compared to EEG, when pretty much you get the signal, you do the pre-processing, you classify good, bad, boom, here is your signal, here are the standard methods for extracting the features, and then do whatever you want with labels and your scenario. So it's novel, and this is why we in research are interested in that way of obtaining, indirect way of obtaining the brain activity.
Mm-hmm. Yeah, definitely. I mean, when we were developing this new functionality and providing an application for people to use, it felt like, it was 15 years ago, like when we started working on this technology, and feeling like we really didn't have a lot of data to go on to be able to build the first applications of this. But we're super excited that this is going to change very, very fast now that we have the device in the field that lots of people are using, because the prospect of now actually having a sizable data set to, train models, so we can start to, see through the particularities of fNIRS. There's many challenges with fNIRS to start to understand where the true signals are. That's very exciting. And if you have any ideas about tasks that could be very interesting to deploy to start to facilitate building a better data set to unravel these things, we're all ears. And there's a lot that we can actually do, without too much difficulty in the application.
I will send you a link to our paper with Dimitra. It is a workload estimation in a very specific scenario. It's a virtual reality flight simulator.
Mm-hmm.
But if we can collect data and do a reliable measurement of the workload with a portable and easy to use device like Muse, then this literally broadens the applications, because workload estimation is an important research tool. In our particular case, we have a closed loop training system, which allows us to speed up the training of the pilots in the flight simulator. But and it's basically bulky, it's a full cap plus VR glasses, etc. But if I can use Muse even for user experience research. Is this user interface more intuitive and easier than that one? And you just run two groups using the workload, boom, you get the answer without basically doing interviews, without humans introducing noise with their answers. You get objective measure of the workload. So that's pretty much something which I will try to find proper resources and to do data collection in another round of measuring the workload. But you guys are in a position to be the first to get a nice and cool generalized model of fNIRS activity of human beings, simply because of that stream of data coming to your lab.
Yeah, totally. And also the combined, fNIRS plus EEG is very interesting. Very, very interesting. And then we haven't detailed any experiments for this, but we can do simultaneous EEG, fNIRS, and ERPs. And it's very interesting to see also how some of the ERP measurements may correlate as well.
In our case, in our paper with Dimitra, actually ECG played a critical role, because fNIRS signal is highly correlated with ECG anyway. If nothing else, we compute the correlation function between ECG and the fNIRS signal, and can easily remove out the bad segments when there is low correlation. ECG is easy to obtain, it's reliable, and if there is low correlation, simply put that fNIRS sensor or channel is somehow flaky and didn't work well.
Mm-hmm. Yeah, so our sort of fNIRS array, it has two short channels as well, and that's something that we also use to try to assess the signal quality of the components, just looking at those correlation coefficients between the different optodes.
Mm-hmm.
But yeah,
I saw that you have a different distance, which means different depth, depth of the penetration.
That's right.
Is this on purpose, or you have a specific reasons for that?
Oh, no, that's on purpose. Yeah. So there's a emitter optode in the middle of the forehead, and then there's a long distance optodes that are about 3 centimeters away, and then there are two optodes that are very close. So you have this sort of like hemispheric symmetry, and then you also have these two short channels. And short channel correction is obviously quite important for fNIRS to be able to extract the sort of the surface blood flow dynamics from the deep tissue.
So in our case, we use it 1.25 centimeters distance between the between transmitters and receivers that happen to be the, okay, at least for the upper part of the head, happen to be the most informational penetration and depth. That's very cool. I'm trying to secure some resources, and you'll be one of the first to knock on your door to get one of the new devices with fNIRS. I'm serious. Just we're super busy this summer, and maybe around the fall, we'll try to organize a device, several devices, and some data collection to see how the things are going to work. Simply because when you estimate workload, it's here. I don't know how reliable we'll be reading from this area. Should be.
Yeah, look, hope you get to do that. I'm looking forward to discovering what you guys find there.
But in general, keeping the device open for researchers will trigger a lot of interesting research on the site using your device. Some of them can be actually easily reduced to business and to be included in your product line, or some of them will be just academic interest of the researchers who are doing the research to publish their paper. Any more questions from the audience, please? I'm afraid I kind of took over the conversation. Colleagues? Questions?
I see some chats at the end, and I see some points on the chat at the end about three general ideas. One was from Dimitra, actually very good questions. How informative would breathing be as opposed to EEG, or added to EEG as opposed to just EEG for tracking awake versus sleep stages?
Yeah,
So that's yeah. Go ahead.
That's a really great question. I mean, I guess it's good to note that the models that we use are EEG only currently, and there's tons of data available as we look at the sensor fusion. One of the challenges is when you're already at an expert level, this question of can you do better is hard to know, and you need to start taking another approach at how you assess the quality of the algorithm, because you're now sort of stretching beyond being able to have a reliable baseline of what is better. So in the case of this digital sleeping pill, the thing that really allowed us to stretch beyond was to really be able to get this in the field and be able to collect user reports of the conscious experience that people have. And this makes sense because you're going through a semi-conscious state, and people's subjective experience actually has a lot of relevance there. But in the data, we get great breathing data both in the head telemetry, so the IMU data, as well as the cardiorespiratory data that comes through the PPG. And I think there's a wealth of possibilities. I'd love to hear, Dimitra, if you have thoughts around if you have a specific idea of what you might look at, what kind of experiment you might do. But I think anyone who's really paid attention to a human being going to sleep, there is like a really interesting things that happen in that respiratory process as you fall asleep. Like you can almost just, oh, you're asleep now. So clearly there's some very special relationships happening there.
It does actually. When we collected that data and started to look at the feature set, of course, we did ablation study, removing the groups of features. And for our biggest surprise, ECG was not that informative, simply because there is plenty of heart information in the fNIRS signal itself. But surprisingly enough, breathing somehow provided interesting information, at least as far as the workload is concerned. So we removed the ECG, but we kept the breathing signal.
Yeah. Yeah, our respiration is very much tied to our autonomic response and our attention. And yeah, it's very, very, very interesting. And when you're coaching people, one of the first things you do is you actually coach people on their breathing because of that. It's a really amazing window into that, your state of consciousness and your emotional state. And you can also facilitate change by just getting someone to focus on this and do subtle repatterning of these things. So I think, yeah, I'm very much interested in the breath also because of this. And it's very interesting. Like, we've obviously spent many years studying the impacts of meditation on the brain. And it's very interesting that the simplest meditation exercise, they call it focused attention, and it is just to pay attention to your breath and to try to observe that without controlling it. And that closed loop of, can you let yourself breathe without interfering, is extremely interesting. Both on an individual level, but also in terms of, trying to unpack, what is someone's moment-to-moment experience.
There is one more reason, at least I think. In general, the heart operates independently of the central nervous system. It's just 6 neurons in a loop, and it depends only on the oxygenation of the blood. While breathing is still consciously or subconsciously controlled by the brain. And it's not out of question that this actually brings certain information about the brain state.
Yeah, there's definitely a lot of action back and forth, absolutely, of the evoked responses that it would have, but also generic whole brain changes it will have from heart to brain. Absolutely, that would further complicate it. I saw an interesting point from Dimitra at the end on the chat as well. It was the fact that, as a general observation, most of the recent EEG self-supervised learning and EEG foundation model literature appears that the folks don't look at noise artifacts, those from the instrumentation, those from the lab environment, those from the task. And they just go towards the embedding space, not keeping into account those sources of the artifacts or artifactual data that would change this embedding space. How do we avoid this becoming the norm that would certainly affect the citizen science platform heavily? That's a great question, something that we've been talking about amongst ourselves as well. We, as Aravind highlighted, we have wealth of signal processing classifiers, basically, a lot of signal quality evaluation models that we try to apply in different situations. So we have a wealth of the data, that large data set that has 2 effects. One, we see a lot of those different noise sources. So from headbands that may be malfunctioning, a headband that's super old, electrodes maybe falling apart. We know how that will affect our data. Or if the subject moves, we have different sensors. We have sensors for that, and we can control for that for those epochs as well, for instance. And there's a lot of those different signal quality classifiers that we apply to our data. And with that wealth of the number of sessions and epochs, we can afford to drop a lot of those epochs as well. So as I said, large amounts of data, and this long period of time we've been looking at it gives us the insight as to what data would be bad. And second, the high number of sessions that would be possible to collect in the wild allow us to drop a lot of data and still remain with a lot of good data, from those 80,000 session samples. So that would be the answer that I would also highlight. Others can speak to this if they want as well.
Maybe one thing I would add, which maybe it's our internal culture at Muse, but we also make a habit of, because we work so much with real-time interventions, we've developed a lot of systems that allow us to simultaneously look at the raw data and also take a look at what our models are predicting. And so we stay very attuned to that sort of input-output reality. And the other thing that keeps us attuned, as Taha said, is we have customers, and they demand that these technologies work flawlessly. And so, we have to stay connected to all the different kinds of challenges that people experience in the field. And, people do a lot of crazy things with the tech. And so I think that's one thing that keeps us real, is, staying connected to what's happening at the end user experience. And also as we develop our algorithms to really stay attuned to what's happening input, output, and at different layers, just so we can continue to develop our own intuition. Because there's many things that are hard to observe in these large models. And, I think, again, like, how do you probe these things to start to learn the intelligence that's been embedded in these models? How do we start to understand, what are their domains of operation that are helpful? And there's a lot of interesting experiments that we can do to now connect real people to these things, to try to help, the humans in the loop probe the learning. Dimitri, did our sort of commentary at all address some of the thoughts that you were having? Do you have other ideas about what we might do to help to keep it real, so to speak?
Basically, part of keeping it real means not to create hype where there is none. And so a lot of recent studies that we see published, 90% classification with just EEG, 98% classification in emotional state. And they create this sort of hype. And if you start drilling into it, or if you start looking at your data, for example, we have so many studies that we decided not to publish because we noticed that there's a certain biased noise from the task the user is performing at the time of recording EEG. We had a task for some stress detection, right? And then there was some systematic signature that was happening when the user is about to press the key in the keyboard to actually, right, show you some results on the task. And we noticed that this is basically what the algorithm is capturing rather than some real. And so, we started noticing the last maybe year or two, every time we talk to people at the conferences, just no one looks at these kind of systematic biases that may be in the data. No one even looks at the raw recordings at all anymore. We just feed it all in the network. And I wonder if the conjunction of an LLM could help highlight where these systematic biases may be.
Totally. Yeah, I so agree with you. And I mean, to be honest, it's really, we don't know how capable the models we're training really are. And so, you get a result, and our first question is it real? And I think we spend, it feels like at least 75% of our time going like, okay, did we measure a real thing, or did we classify something that is making us believe it's doing the right thing and it's actually not? And man, it's like that problem is fraught with so many challenges, and I totally agree with you, especially when you're dealing with something that has this complexity and no one knows what it's capable of yet.
Yeah.
So we're running out of time. We didn't have, obviously this discussion and interaction will continue. We didn't have time to discuss the digital sleeping pill, but I just want to underline how important and prospective is this. In general, closing the loop of the human-machine interface is a wow thing. And it doesn't matter that you don't talk directly to the brain, but through audio or to something else. Computer brain is a super prospective thing, and we will see further development in that area. But just wanted to underline that I'm super excited in the very existence of those closed loop interfaces. We do this in the workload, in the training process. You guys do it in the process of falling asleep, but that's a wow thing, and we strongly believe that there is a huge potential in this story. Any last questions from the audience? If not, let's thank our speakers. It was a super interesting session. Thank you so much for this talk and for the discussion, and I'm pretty sure our interaction will continue. Okay?
Thank you, Ivan, for the invitation.
Great.
Thank you, guys. See
Thank
you.
you,
Bye-bye.
everyone. Bye-bye.